Hello everyone, welcome back to Regents Chemistry Review Series. In this video, we're going to talk about chemical reactions. So, what are chemical reactions? Chemical reactions are when we have two or more chemicals that undergo some sort of chemical change, and so they are not the same. So there is a change in the chemical composition. So what are some of the things that represent that a chemical reaction is occurring? So some things that serve as the evidence of a chemical reaction are if you see a color change, or if you see some sort of a precipitate forming, if you see any gas bubbling. Another fancy word that we use for bubbling is effervescence. So if you see some sort of effervescence, that is also an evidence of chemical reaction. If you notice that the reaction is releasing heat or absorbing heat, then that also represents a chemical reaction. There are 5 types of chemical reactions that we are going to talk about in this lesson, and those are synthesis, decomposition, single replacement, double replacement, and combustion. So let's start off with the first few. So the synthesis reaction is when we have two simpler substances that are combining to make a complex substance. Please make sure that you remember this definition in the same terminology. Simpler substances combining to make a complex substance. So in this case, because we are forming the bonds, so whenever we form the bonds, energy is released. So it is an exothermic reaction. So here are some examples of your synthesis reaction. Decomposition is when a complex substance breaks down into simpler substances. So in this case, because bonds are broken, the system needs to absorb energy to break the bonds. This one represents an endothermic reaction. So here are some examples. Then we have the combustion reaction. So this is the type of reaction where we have a carbon-based compound, and the carbon-based compound reacts with oxygen, and the two products are carbon dioxide and water. Please remember that all of these parts are very, very important for something to be a combustion reaction. So if you are given a reaction where some random thing is combining with oxygen, that is not a combustion reaction. So you need to have a carbon-based compound reacting with oxygen, and you need to have carbon dioxide and water in your products. Otherwise, it's just some other type of reaction. It's not combustion. So here are 2 examples. You are given a lot more examples of the combustion reactions in table I. So I believe the first 6 are combustion reactions. All right, so the next the last two types of chemical reactions that we're going to talk about are single replacement and double replacement. So single replacement is when we have a free element, or just an element that is in the elemental form that replaces a different element which is in a compound. Here is an example of that reaction. So we see that iron in this compound is replacing copper. So iron is in elemental form, copper is in a compound. So double replacement, on the other hand, is when we have 2 species that replace each other, or they switch their partners. And so the examples that are given here, there's only one example actually, is when we have sodium chloride combining with silver nitrate. So the sodium and silver, they are both replacing each other. So this will be your double replacement reaction. So look, for single replacement and double replacement reactions, we are also going to talk about if the reactions are actually going to occur, because they don't always occur. So if you look back at the single replacement reaction, what must happen for a single replacement reaction to occur? So what you need to remember is that for any single replacement reaction to occur, we must have a more reactive metal replacing the less reactive metal. And to figure out how active metals are compared to the other metals, we look at table J. So going with the example that we discussed earlier, you notice that iron is kind of above the copper. So this means iron is more active and copper is less active. So because iron is more active, it can replace copper. Copper, however, cannot replace iron. Okay, so because iron can replace copper, that means this reaction will occur. But as I mentioned, if I switch this reaction just a little bit and write it like this, where we have copper in the elemental form and iron is in the compound. Now, because copper is less active than iron, copper cannot replace iron, so this reaction will not occur. So now let's talk about double replacement reactions. How do we know that these reactions will occur? So for a double replacement reaction, we must have a precipitate in the products. So that means we're going to have to look at the solubility guidelines that are given to us in table F. So if you go ahead and open table F, remember that we are looking for a precipitate in the products. So you are going to look at both of your products, the sodium nitrate and the silver chloride, and you're going to figure out if either one of these two is going to make a precipitate. It will make a precipitate if it's insoluble, right? So here is your table F, just half of table F, it's not the whole thing. So if you look at table F, let's start with sodium nitrate. You notice that sodium is part of the group 1 ion. So table F says that group 1 ions are always soluble. There are no exceptions to that. Nitrate is also always soluble. No exceptions to that as well. So that means sodium nitrate is soluble. If you look at silver chloride, your table F says that chlorides, which are halides, are always soluble except when they combine with silver, lead, or mercury. So in this case, because our chloride is combining with silver, it's going to be insoluble. So that means silver chloride is going to be the precipitate in this reaction. Now, because we are forming a precipitate, that means the reaction will occur. If both of our products turn out to be soluble, that means the reaction will not occur. Okay, so that's how we figure out whether a single and a double replacement reaction will occur or not. The next thing that we want to talk about the chemical reactions is how do we balance the chemical equations. So the thing to remember is that in any chemical reaction, we follow the law of conservation of matter, meaning the mass, energy, and charge, everything must be balanced in a chemical reaction. So this should be the same on both sides. So when you are balancing your chemical equations, you want to make sure that the number of atoms of each element should be the same on both sides. So let's take at some examples. Here's the first one. We see that on the reactant side, we have 4 phosphorus, we have 2 oxygens. On the product side, however, we have let me write 4 phosphorus, 2 oxygen. On the product side, however, we have 2 phosphorus and 5 oxygens. So let's go ahead and maybe start balancing the phosphorus first, right? So if we want to balance the phosphorus on the product side, we're going to have to multiply this with the 2. Okay, so if you are multiplying this with a 2, that means I'm going to add a coefficient of 2 with the phosphorus. So that gives me 10 phosphorus on this side and 4 phosphorus on this side and 10 oxygens on this side. Okay, now the phosphorus is balanced on both sides. However, so we can go ahead and maybe cross off the phosphorus for now, but our oxygens are not balanced on both sides. So we have 10 oxygen in the products and only 2 on the reactant side. So if I want to balance the oxygens on the reactant side, I'm going to have to go ahead and multiply my oxygens on the reactant side with a 5. So in this case, I'm going to put a 5 with the oxygen. This is going to have no impact on the phosphorus because they are both separate from each other. So that's going to give us 10 oxygens. So now the oxygens are balanced as well. Okay, so this is how we balance the equations. Let's look at, so this is going to be your balanced chemical equation. Let's look at another example. So here we have this one. We can go ahead and maybe make a table for all of them. So let's do carbon, we have hydrogen, we have oxygen. These are the three elements that we have on both sides, right? So in this case, we have 3 carbons on the reactant side, and we have 8 hydrogens on the reactant side, and we have 2 oxygens. On the product side, we've got 1 carbon, and we have 2 hydrogens, and we have 1, 2, 3. We've got 2 oxygens here, 1 oxygen there. Let's just make a line there, okay? So now we can go ahead and start off with whatever you like, but in most cases it will be whenever you're looking at a combustion reaction, it's normally a good idea to start with carbon. So maybe we want to start balancing off the carbon. So we have 3 on the reactant side, 1 on the product side. So let's go ahead and multiply this with a 3. So I'm going to add that 3 over here. So that gives me 3 carbons on the reactant side, and 3 times 6, that is 6 oxygens here. Okay, so now that carbon is balanced, let's look at your hydrogens next. We have 8 on the reactant side, we have 2 on the product side. So maybe multiply this with a 4 so that I have 8 hydrogens here, and we have 4 oxygens here. So now we can go ahead and look at our oxygens. We have 6 times 4, 6 plus 4, we have 10 in the product side. We only have 2 on the reactant side. So multiply this with a 5, and that is going to give me 10 on the reactant side. So now everything looks the same on both sides, and here is your balanced chemical equation. All right. So then some other important concepts that we need to remember about the chemical reactions is sometimes you might be asked to determine the mass, and we have to use the law of conservation of mass for these type of questions. So here's an example. You're given a reaction, and they are saying how much oxygen is needed to react with 4.5 grams of C3H8 to produce 2.8 grams of carbon dioxide and 5.2 grams of H2O. So you know that according to the law of conservation of mass, the total mass of the reactants should be equal to the total mass of the products, right? So we start off by writing the equation, and we write all of the masses that are given in the question. So we have 4.5 grams of C3H8. We don't know the mass of oxygen. We have 2.8 grams of carbon dioxide, 5.2 grams of water. So if we add the mass on the product side, we happen to have 8 grams in the product side, and right now on the reactant side we only have 4.5 grams. So if we want them to be equal, we solve for x, and that turns out to be 3.5 grams, because 4.5 plus 3.5, that gives us 8 grams on the reactant side, and we're going to have 8 grams on the product side. The second important concept that you need to remember is sometimes you might be asked to determine the missing reactants or products. For example, here you have to determine the products and write a balanced chemical equation for this reaction. The first thing that you're going to have to do is determine the type of chemical reaction. So we know that we have an element in the elemental form which is reacting with a compound. So this is a single replacement reaction. Then we are going to write the products. And remember that if we are making an ionic compound in the products, we want to make sure that we have the correct formula. So we want to have the correct subscripts. And then we just balance the equation. So let's write our products first. So in this case, we know that magnesium is going to replace zinc. So that means we are going to get zinc in the elemental form. And so when magnesium is reacting with sulfate, magnesium has a charge of +2 and sulfate has a charge of -2. So when these two, when we do the crisscross, we bring the 2 down for both of them. So the chemical formula that we get for this is going to be Mg2SO4 2. So now remember, when both of your subscripts are the same, we can write the simplest ratio between both of them. So it's just going to be MgSO4. Okay, so there you go. Those are your products for this reaction. All right, Lastly, we want to talk about stoichiometry in chemical reactions. So, stoichiometry is kind of the quantitative relationship between the amount of reactants and products, because what happens in a chemical reaction is that if we change the quantity of one thing, it is going to change the quantity of everything else in the reaction. So, to work with stoichiometry problems, we need to work with something called the mole ratio. And mole ratio depends on the coefficients of the substances that we have in any reaction. So let's look at this example. We have 2H2 plus O2, that gives us 2H2O. So if I ask you for the mole ratio between hydrogen and oxygen in this example, it's going to be 2/1. If I ask you for the mole ratio between hydrogen and water, that's 2/2. So it's just 1. If I ask you for the mole ratio between oxygen and water, that's going to be 1/2. Okay, and something else that we need to know about stoichiometry is the relationship or the conversion between mole to mass. We have talked about this already. You are given the equation to go between moles to mass. It's given in table T. So if you're given the mass and you want to go to moles, you can use this equation, which is given in table T. So number of moles is equal to the given mass divided by the molar mass, or the gram formula mass. If you're given the moles and you want to convert that to the mass, we can just rearrange the same equation, and we want to solve for the mass, let's say. So we are just going to multiply the moles with the gram formula mass, and that is going to give us the mass. So let's look at some type of problems that we can get for stoichiometry. So you can either have the mole to mole problems, which means you'll be given the moles of something in your equation or chemical reaction, and you'll be asked to find the moles of the other thing. So here you're given an equation. It's asking how many moles of calcium are needed to react completely with 6 moles of water. So the thing to remember here is that we are only dealing with calcium and water in this equation. So we are not concerned with calcium oxide or hydrogen at all. Okay, so you can just ignore them for now. So if you want to go from moles of water to moles of calcium, the first thing that we want to do is figure out the mole ratio. So mole ratio between calcium and water is that we have, for 1 mole of calcium, we are using 2 moles of water. Okay, and so the second thing that we want to do is set up a proportion, or set up like a dimensional analysis kind of thing. So we want to start with what's given. So we have 6 moles of water, and we want to multiply this with our mole ratio. So remember that we want to cancel out the moles of water, so that's why we're going to put 2 moles of water at the bottom, and we're going to put 1 mole of calcium at the top. So the moles of water cancel out with the moles of water, and then 6/2, that gives us 3 moles of calcium. So this is how many moles of calcium we need to react with 6 moles of water. Okay, and then sometimes we can also be given the moles, and we'll be asked to convert that to mass, or we'll be given the mass and we'll be asked to convert that to moles. So in this case, we have the same equation again, and they are saying how many grams of calcium are needed to react completely with 8 moles of water. So once again, we want to figure out the mole ratio first. So we know that 1 mole of calcium is equal to 2 moles of water. And we are not dealing with calcium hydroxide or water or hydrogen in this case, so we are just ignoring them. And then we're going to start with 8 moles of water in this case, and we are going to multiply that with the mole ratio. So because I want to cancel out the moles of water, so I'm putting 2 moles of water at the bottom and 1 mole of calcium at the top. So moles of water cancel out with the moles of water, and we get 8 over 2, that is 4 moles of calcium. Now here's the thing, this only gave us the moles, but the question is asking for the grams of calcium, right? So what we can do now, if you want to go from moles of calcium to grams of calcium, is that we can use the gram formula mass. So gram formula mass of calcium is 40 grams per mole. And I got this from the periodic table. This is the atomic mass of calcium. So I'll say that if I have 4 moles of calcium, then I'm going to multiply this with the gram formula mass. So the gram formula mass tells me that 1 mole of calcium has 40 grams of calcium. So you're just going to do 4 times 40, and that is about 160 grams of calcium that we need to react with 8 moles of water. Okay, so that was your stoichiometry problems. These are the 2 types of problems that you're going to get. So just remember that the main thing is to cancel the units. And just keep in mind what the question is asking for, and then kind of ask yourself what are the things that you need to go from what's given in the question to what you need. Alrighty, so that's it for this unit. I will see you in the next one.